Right now, you are surrounded by trillions of invisible quantum guardians enforcing the most fundamental law in the universe. Every atom in your body, every breath you take, every star burning in the night sky exists only because of a single quantum rule discovered exactly 100 years ago. This rule prevents all matter from collapsing into nothingness and determines why you have a physical form instead of being a puddle of quantum soup on the floor. In December 1924, a brilliant Austrian physicist named Wolfgang Pauli submitted a paper that would forever change our understanding of reality itself. He discovered that electrons follow an unbreakable cosmic law, a quantum commandment so absolute that violating it would cause the entire universe to collapse into chaos. This discovery earned him the Nobel Prize and gave us the key to understanding why atoms exist, why chemistry works, and why solid matter has any structure at all. If you enjoy discovering the hidden rules that govern reality, hit that like button because what I'm about to reveal will fundamentally change how you see the physical world around you. Today, we're diving deep into the Pauli Exclusion Principle, the quantum law that literally holds everything together. Here's what makes this principle so mind-bending. Imagine trying to fit two people into the same chair at exactly the same time. In our everyday world, this seems impossible because of physical space limitations. But in the quantum world, particles don't follow our intuitive rules about space and matter. Quantum particles can exist in multiple places simultaneously, tunnel through solid barriers, and behave in ways that defy common sense. Yet even in this bizarre quantum realm, there exists one absolute rule that cannot be broken. The Pauli Exclusion Principle states that no two identical particles with half-integer spin can occupy the same quantum state simultaneously. This might sound like abstract physics jargon, but the implications are staggering. Every single property of matter that makes your existence possible flows directly from this one quantum law. Before Pauli's discovery, scientists were puzzled by a fundamental mystery. They understood that electrons orbit atomic nuclei, but they couldn't explain why atoms had the specific structures observed in nature. Why did hydrogen have one electron while helium had two? Why did the periodic table follow such precise patterns? Why didn't all electrons simply crash into the nucleus and occupy the lowest possible energy state? Wolfgang Pauli realized that electrons possess an intrinsic property called spin, and this spin creates an invisible quantum fingerprint that makes each electron unique. Think of it like a cosmic no two electrons identification system where can share identical quantum credentials. Each electron must have a unique combination of quantum numbers that describe its energy level, orbital shape, magnetic orientation, and spin direction. The mathematical beauty of this principle emerges when you consider what quantum numbers actually represent. Every electron in an atom is described by 4 quantum numbers. The principal quantum number determines the electron's energy level and distance from the nucleus. The azimuthal quantum number defines the shape of the electron's orbital. The magnetic quantum number specifies the orbital's orientation in space. Finally, the spin quantum number indicates whether the electron spins up or down. For 2 electrons to violate the Pauli exclusion principle, they would need identical values for all 4 quantum numbers simultaneously. The principle declares this impossible. Nature has built an absolute prohibition into the fabric of reality itself. This quantum law reveals something profound about the fundamental nature of particles. In quantum mechanics, particles are classified into 2 categories based on their spin properties. Particles with half-integer spin, called fermions, must obey the Pauli exclusion principle. These include electrons, protons, neutrons, and quarks. Particles with integer spin, called bosons, can share quantum states and include photons, certain atomic nuclei, and force-carrying particles. The distinction between fermions and bosons creates the entire architecture of matter. Fermions form the building blocks of atoms and molecules, while bosons transmit forces between particles. Without this fundamental division, the universe would be a chaotic soup of indistinguishable particles with no stable structures. The exclusion principle manifests most clearly in atomic structure. Consider the simplest atom, hydrogen, with a single electron orbiting its nucleus. This electron occupies the lowest available energy state, called the 1s orbital. Now examine helium, which contains two electrons. Both electrons want to occupy that same low-energy 1s orbital, but the Pauli exclusion principle prevents them from having identical quantum states. Nature's solution is elegant. The two helium electrons can share the 1s orbital only if they have opposite spins. One electron spins up while the other spins down, giving them different spin quantum numbers. This arrangement satisfies the exclusion principle because the electrons now possess different quantum fingerprints. But what happens when you add a third electron, as in lithium? The 1s orbital is already full with two electrons of opposite spins. The Pauli exclusion principle forces the third electron into a higher energy level, the 2s orbital. This creates the first electron shell beyond the innermost level. As you continue adding electrons to build heavier atoms, the exclusion principle forces electrons into increasingly complex arrangements. Each orbital can hold a maximum of 2 electrons with opposite spins. When orbitals fill completely, additional electrons must occupy higher energy levels, creating the elaborate shell structure that determines chemical behavior. This electron shell filling pattern directly explains the periodic table's organization. Elements in the same column have identical numbers of electrons in their outermost shells, giving them similar chemical properties. The exclusion principle literally creates the foundation for all chemistry by determining how atoms can share or transfer electrons during chemical reactions. The quantum mechanical foundation underlying the exclusion principle reveals even deeper truths about reality. Fermions are described by antisymmetric wave functions, meaning their mathematical descriptions change sign when two identical particles are exchanged. This antisymmetry requirement has profound physical consequences. When two fermions approach each other, their wave functions must remain antisymmetric. This creates an effective repulsive force that keeps identical fermions separated even when no classical forces are present. Physicists call this quantum mechanical effect exchange interaction or Pauli repulsion. Pauli repulsion explains why solid matter has volume and resists compression. The electrons in adjacent atoms cannot occupy identical quantum states, so they maintain separation distances that give objects their physical size. Without the exclusion principle, all electrons would collapse into the lowest energy states, and matter would have no stable structure. This quantum repulsion operates on scales ranging from individual atoms to stellar objects. In white dwarf stars, gravity compresses matter to incredible densities, but electron degeneracy pressure created by the Pauli exclusion principle prevents further collapse. The exclusion principle literally holds these stellar remnants together against gravitational forces that would otherwise crush them into black holes. The principle extends beyond individual atoms to determine the electronic properties of solid materials. In metals, semiconductors, and insulators, vast numbers of electrons must occupy different quantum states according to Pauli's law. This creates energy band structures that determine whether materials conduct electricity, block current flow, or exhibit semiconducting behavior. Modern technology depends entirely on our understanding of how the exclusion principle governs electronic behavior in solids. Computer processors, LED displays, solar panels, and countless other devices function because engineers can manipulate electron distributions while respecting the fundamental quantum constraints discovered by Pauli. Even the stability of matter itself emerges from the exclusion principle. Without this quantum law, electrons would cascade into the lowest available energy states, causing atoms to collapse and releasing enormous amounts of energy. The principle prevents this catastrophic outcome by maintaining the electron shell structures that define chemical elements. Recent experimental tests continue to probe the limits of the Pauli exclusion principle's validity. Scientists search for violations by looking for forbidden quantum transitions that would indicate the principle breaking down under extreme conditions. These experiments place increasingly stringent limits on any possible violations, confirming that the principle appears absolutely fundamental to physical reality. The principle also connects to deep questions about the nature of identical particles in quantum mechanics. All electrons in the universe possess exactly identical properties, according to our current understanding. This means the exclusion principle technically applies to all electrons everywhere, though practical considerations limit its effects to particles in close proximity. The mathematical formulation underlying the principle emerges from quantum field theory and the spin statistics theorem. This theorem proves that particles with half-integer spin must obey antisymmetric statistics, while integer spin particles follow symmetric statistics. The connection between spin and statistical behavior represents one of the most profound relationships in fundamental physics. Understanding the Pauli exclusion principle opens doorways to comprehending how quantum mechanics governs the macroscopic world we experience daily. The principle bridges the gap between abstract quantum theory and tangible physical phenomena, showing how quantum laws determine the properties of matter on every scale from subatomic particles to cosmic structures. The implications become even more extraordinary when you examine what happens inside neutron stars, the most extreme objects in the universe beyond black holes themselves. When a massive star explodes in a supernova, the core gets compressed to densities so extreme that protons and electrons are literally crushed together, forming neutrons. These neutrons, also being fermions, must obey the Pauli exclusion principle just like electrons do. Inside a neutron star, matter reaches densities exceeding 100 million tons per cubic centimeter. At this point, the neutrons themselves become degenerate, meaning they're packed so tightly that quantum mechanics takes over classical physics entirely. The Pauli exclusion principle creates what scientists call neutron degeneracy pressure, and quantum mechanical force so powerful it can support the weight of 1.4 times our sun's mass in a sphere only 12 miles across. Think about what this means for a moment. The same quantum law that determines why your coffee cup has a solid structure is also preventing neutron stars from collapsing into black holes. The exclusion principle operates across 30 orders of magnitude in scale, from individual atoms to objects containing more mass than our entire solar system. But here's where the story takes a dramatic turn. The Pauli exclusion principle doesn't just prevent collapse, it actually creates entirely new states of matter that cannot exist under normal conditions. In the cores of neutron stars, pressures become so extreme that even neutron degeneracy pressure begins to fail. Scientists predict that exotic forms of matter emerge, possibly including free quarks existing outside of protons and neutrons for the first time since the universe was microseconds old. These quark stars would represent matter in a state so alien that the very concept of atomic structure breaks down completely. Yet even here the exclusion principle continues operating. Quarks themselves are fermions, so they too must obey Pauli's quantum commandment. The principle that governs the electrons in your fingernails also determines the behavior of matter under conditions more extreme than anything that existed during the first moments after the Big Bang. The exclusion principle reveals something profound about the nature of information in the universe. Each quantum state represents a unique piece of information about a particle's properties. The principle essentially declares that nature cannot compress this information beyond certain fundamental limits. Two fermions cannot share identical information signatures, creating an absolute constraint on how efficiently matter can be packed together. This information theoretic aspect connects to cutting-edge research in quantum computing and cryptography. Quantum computers exploit the fact that fermions must maintain distinct quantum states to perform calculations impossible on classical machines. The exclusion principle that prevents electrons from occupying identical states also enables quantum processors to maintain the delicate superposition states needed for quantum algorithms. Scientists are discovering that the principle extends far beyond simple particle interactions. In quantum many-body systems, where thousands or millions of particles interact simultaneously, the exclusion principle creates complex emergent behaviors that cannot be predicted from studying individual particles alone. These collective quantum effects give rise to phenomena like superconductivity, superfluidity, and quantum magnetism. Superconductivity provides a perfect example of how the exclusion principle enables seemingly impossible behaviors. In superconducting materials, electrons form pairs called Cooper pairs that behave as composite bosons rather than individual fermions. Since bosons can share quantum states, these electron pairs can all occupy the same quantum state, creating a macroscopic quantum phenomenon where electrical current flows without resistance. The formation of Cooper pairs represents a fundamental transformation in how particles obey quantum statistics. Individual electrons must follow the exclusion principle, but when they pair up under specific conditions, the composite system follows entirely different rules. This demonstrates how the same quantum law can enable both the structure of ordinary matter and the exotic behaviors observed in quantum materials. Recent discoveries in condensed matter physics reveal even more bizarre consequences of the exclusion principle. Researchers have created artificial materials where electrons behave as if they exist in curved spacetime, similar to the geometry around black holes. In these exotic materials, the exclusion principle combines with engineered crystal structures to create phenomena that mirror some of the most extreme environments in the universe. Scientists have also discovered topological phases of matter where the exclusion principle creates protected quantum states that cannot be destroyed by ordinary disturbances. These topological materials could revolutionize quantum computing by providing inherently stable quantum bits that maintain their information even in the presence of environmental noise. The principle's effects on chemical bonding reveal another layer of complexity in how quantum laws shape our world. When atoms approach each other to form molecules, their electron clouds begin to overlap. The exclusion principle prevents electrons from occupying identical states, creating regions of space where electron density must decrease. These quantum mechanical holes in electron density actually contribute to the attractive forces that hold molecules together. This quantum bonding mechanism operates alongside electrostatic attractions to create the diverse world of chemical compounds. The exclusion principle doesn't just determine which electrons can occupy which orbitals, it actively participates in creating the forces that bind atoms into molecules. Every chemical reaction involves redistributions of electrons that must respect Pauli's quantum constraints. The principle also explains why certain chemical reactions occur spontaneously while others require enormous amounts of energy. When electrons rearrange during chemical reactions, they must find new quantum states that satisfy the exclusion principle. Some rearrangements allow electrons to occupy lower energy states while maintaining distinct quantum signatures. Others force electrons into higher energy configurations, making reactions energetically unfavorable. Understanding how the exclusion principle governs chemical behavior has enabled chemists to design molecules with specific properties for applications ranging from pharmaceuticals to advanced materials. By predicting how electrons will arrange themselves while obeying quantum constraints, researchers can engineer compounds with desired electrical, optical, or mechanical characteristics. The biological implications of the exclusion principle extend throughout living systems. DNA molecules maintain their double helix structure partly because of quantum mechanical forces arising from electron arrangements that respect Pauli's law. The specific hydrogen bonding patterns that hold DNA strands together depend on electron distributions determined by the exclusion principle. Protein folding, the process by which amino acid chains adopt their functional three-dimensional shapes, also involves quantum mechanical effects related to the exclusion principle. The forces that guide proteins into their correct conformations include quantum mechanical interactions between electron clouds that must maintain distinct quantum states. Even photosynthesis, the fundamental process that converts sunlight into chemical energy, relies on quantum effects related to particle statistics and the exclusion principle. In photosynthetic complexes, electrons excited by light must navigate through molecular structures while obeying quantum constraints. Recent research suggests that quantum coherence effects, ultimately rooted in the fundamental statistics of fermions and bosons, contribute to the remarkable efficiency of photosynthetic energy transfer. The exclusion principle's role in determining the periodic table's structure has implications that extend far beyond chemistry textbooks. The arrangement of elements by atomic number directly reflects how electrons fill atomic orbitals according to Pauli's constraints. This arrangement predicts not just chemical properties, but also nuclear stability, radioactive decay patterns, and the formation of elements in stellar interiors. Heavy elements beyond iron can only form through neutron capture processes in dying stars and stellar explosions. Even these extreme nucleosynthesis processes must respect the exclusion principle as neutrons and protons arrange themselves in nuclear configurations. The principle helps determine which isotopes can exist stably and which undergo radioactive decay. The study of superheavy elements, with atomic numbers exceeding 100, pushes the boundaries of how the exclusion principle operates under extreme conditions. These artificial elements exist for only fractions of a second before decaying, but their brief existence provides insights into how quantum laws govern matter at the limits of nuclear stability. Scientists predict that somewhere around element 114 or 126, there might exist an island of stability where superheavy nuclei become relatively long-lived. The existence and properties of these hypothetical elements depend critically on how the exclusion principle governs the arrangement of protons and neutrons in extremely heavy atomic nuclei. The principle's universality raises profound questions about the nature of physical law itself. Every electron in the observable universe, whether in your body or in a galaxy billions of light years away, must obey exactly the same quantum constraints. This suggests that the exclusion principle represents something fundamental about the mathematical structure underlying physical reality. Some physicists speculate that the exclusion principle might be connected to the deepest levels of spacetime geometry, in theories that attempt to unify quantum mechanics with general relativity. The statistics of fermions and bosons emerge from the fundamental topology of spacetime itself. The principle might reflect basic constraints on how information can be encoded in the fabric of the universe. These connections between quantum mechanics and spacetime geometry could have implications for understanding black holes, where matter reaches densities so extreme that even neutron degeneracy pressure fails. Inside black holes, the normal rules of spacetime break down, but the fundamental quantum constraints embodied in the exclusion principle might still apply in some modified form. The principle continues to surprise scientists with new applications and unexpected consequences. Recent theoretical work suggests that the exclusion principle might play a role in cosmic inflation, the hypothetical rapid expansion of space during the universe's first fraction of a second. If true, the same quantum law that determines atomic structure might also have shaped the large-scale structure of the cosmos itself. Modern experiments continue probing whether the exclusion principle might break down under extreme conditions or over cosmic timescales. Some theories predict tiny violations of the principle that could be detectable with sufficiently sensitive instruments. Finding such violations would revolutionize our understanding of quantum mechanics and potentially point toward new physics beyond the standard model. The search for Pauli exclusion principle violations involves incredibly precise measurements of atomic transitions that should be forbidden if the principle holds exactly. Scientists use underground laboratories shielded from cosmic rays to detect hypothetical signals that would indicate electrons occasionally violating their quantum constraints. So far, these experiments have found no evidence for violations, confirming that the exclusion principle appears to be an exact law of nature. The precision of these tests continues to improve, potentially revealing new physics if the principle shows even the tiniest deviations from perfect exactness. The search for violations has pushed experimental physics to extraordinary limits. Scientists have built detectors so sensitive they can observe individual photons arriving from forbidden atomic transitions. These experiments require isolation chambers buried deep underground, shielded from cosmic radiation that could interfere with measurements. The results consistently confirm that the Pauli exclusion principle operates with mathematical perfection across every scale we can test. But here's where things get truly mind-bending. The exclusion principle doesn't just govern particles we can observe directly. It extends into realms of physics that challenge our basic concepts of reality itself. In quantum field theory, the principle applies to virtual particles that pop in and out of existence in the vacuum of empty space. Even these ephemeral quantum fluctuations must respect Pauli's cosmic law. Virtual particles represent one of the strangest predictions of quantum mechanics. According to quantum field theory, what we call empty space actually teems with particle pairs that spontaneously appear and annihilate within timeframes so brief they cannot be directly observed. These virtual fermions must obey the exclusion principle just like real particles, creating quantum mechanical constraints on the very fabric of space-time. The implications stretch beyond theoretical physics into practical applications that surround you right now. The device you're using to watch this video depends on semiconductor technology that exploits the exclusion principle at every level. Silicon computer chips work because engineers can precisely control how electrons occupy quantum states in crystalline materials while respecting Pauli's absolute constraints. Modern processors contain billions of transistors, each one a quantum mechanical device that switches electrical current by manipulating electron distributions according to the exclusion principle. The same quantum law that prevents atoms from collapsing also enables the digital revolution that defines our technological civilization. The principle's role in determining material properties extends far beyond simple conductivity. Magnetic materials derive their properties from the alignment of electron spins, which must arrange themselves in patterns consistent with the exclusion principle. Ferromagnetic substances like iron become magnetic because unpaired electrons can align their spins in parallel configurations while maintaining distinct quantum states. Superconducting magnets used in medical imaging scanners and particle accelerators rely on quantum mechanical effects that emerge when the exclusion principle combines with other fundamental forces. These materials can carry enormous electrical currents without resistance because electrons form Cooper pairs that collectively behave as a single quantum mechanical entity. The quantum Hall effect, discovered in the 1980s, reveals even more exotic consequences of the exclusion principle. When electrons are confined to two-dimensional surfaces and subjected to strong magnetic fields, they form incompressible quantum fluids with properties unlike any classical material. These quantum Hall states demonstrate how the exclusion principle can create entirely new phases of matter under extreme conditions. Recent discoveries in graphene, a single layer of carbon atoms arranged in a honeycomb pattern, show how the exclusion principle operates in materials with unusual electronic properties. Electrons in graphene behave as if they have no mass, traveling at constant speeds like photons while still obeying fermionic statistics. This combination creates quantum behaviors that were previously thought impossible. The development of quantum dots, tiny semiconducting crystals that confine electrons in all three spatial dimensions, has revealed how the exclusion principle operates when particles are trapped in spaces comparable to their quantum wavelengths. These artificial atoms demonstrate quantum mechanical effects on scales large enough to manipulate with conventional manufacturing techniques. Scientists have discovered that quantum dots can be engineered to emit light at specific wavelengths by controlling how many electrons they contain. Each additional electron must occupy a higher energy level due to the exclusion principle, systematically changing the optical properties of these quantum mechanical structures. The principle also governs the behavior of ultra-cold atomic gases cooled to temperatures within billionths of a degree above absolute zero. At these extreme temperatures, quantum mechanical effects dominate over thermal motion, allowing scientists to observe how large numbers of fermions arrange themselves according to Pauli's constraints. These ultra-cold fermion gases reveal quantum mechanical phenomena that cannot be observed at higher temperatures. Researchers have created artificial materials by trapping atoms in optical lattices formed by intersecting laser beams, allowing them to study how the exclusion principle operates in controllable quantum many-body systems. The study of quantum degenerate gases has led to discoveries about quantum phase transitions, where materials suddenly change their properties as temperature, pressure, or other parameters cross critical thresholds. These transitions often involve fundamental changes in how particles obey quantum statistics while respecting the exclusion principle. One of the most remarkable applications involves using ultracold atoms to simulate the behavior of electrons in exotic materials that cannot be created by conventional means. By mapping atomic properties onto electronic systems, researchers can explore theoretical predictions about quantum materials that might revolutionize technology. The exclusion principle's effects on nuclear physics reveal another layer of complexity in how quantum laws govern matter. Protons and neutrons in atomic nuclei must arrange themselves in shell structures analogous to electron shells, but with different energy scales and quantum numbers. This nuclear shell structure determines which isotopes are stable and which undergo radioactive decay. The magic numbers in nuclear physics, where nuclei with specific numbers of protons or neutrons show enhanced stability, arise directly from the exclusion principle's effects on nuclear structure. These special nuclei have completely filled nuclear shells, similar to noble gas atoms with filled electron shells in chemistry. Understanding nuclear shell structure has enabled scientists to predict they are synthesized properties of super-heavy elements beforeized in particle accelerators. The exclusion principle helps determine how long these artificial elements might survive before decaying and what nuclear reactions might be possible with them. The principle also governs the processes that power stars and create the elements necessary for life. In stellar interiors, nuclear fusion reactions must overcome both electrical repulsion between charged nuclei and the quantum mechanical constraints imposed by the exclusion principle on the resulting nuclear products. The carbon-nitrogen-oxygen cycle that powers massive stars involves a complex sequence of nuclear reactions where protons and neutrons rearrange themselves while respecting quantum statistical requirements. Each step in this cycle must satisfy the exclusion principle's constraints on the final nuclear configurations. Even the formation of neutron stars involves quantum mechanical effects related to the exclusion principle operating on multiple levels simultaneously. As a stellar core collapses, electrons and protons are forced together to form neutrons, but this process must respect quantum constraints on both the initial and final particle states. The resulting neutron star represents matter in a quantum degenerate state, where the exclusion principle prevents further gravitational collapse. The interior of these objects contains matter at nuclear density, where quantum mechanical effects completely dominate over classical physics. Scientists predict that the cores of the most massive neutron stars might contain exotic forms of matter where the exclusion principle operates arc matter phases on free quarks rather than confined protons and neutrons. These Q would represent completely new states of matter that existed briefly during the universe's first microseconds. The exclusion principle extends beyond individual particles to influence the large-scale structure of the universe itself. Dark matter, which comprises most of the matter in the cosmos, likely consists of particles that obey fermionic statistics and therefore must respect Pauli's constraints. Computer simulations of cosmic structure formation must account for the quantum mechanical properties of dark matter particles, including how they distribute themselves according to the exclusion principle. These quantum effects influence how galaxies form and evolve over cosmic timescales. The principle also affects our understanding of black holes, where matter reaches densities so extreme that quantum effects become important even in the presence of intense gravitational fields. Some theories suggest that the exclusion principle might prevent information from being truly destroyed when matter falls into black holes. Recent work on black hole thermodynamics proposes that the information paradox, where quantum mechanics appears to conflict with general relativity, might be resolved by considering how the exclusion principle operates in curved spacetime. The quantum constraints on fermionic matter might preserve information in ways that classical gravity alone cannot account for. These connections between quantum mechanics and gravity represent some of the deepest unsolved problems in theoretical physics. The exclusion principle, discovered through careful analysis of atomic spectra, might hold keys to understanding the fundamental nature of spacetime itself. The principle's universality suggests that it reflects something profound about the mathematical structure underlying physical reality. Every fermion in the observable universe, from electrons in distant galaxies to neutrinos streaming through your body right now, must obey exactly the same quantum constraints discovered by Wolfgang Pauli a century ago. This universal applicability raises questions about why the exclusion principle takes its specific mathematical form rather than some alternative. Theoretical physicists continue exploring whether the principle might emerge from even more fundamental symmetries or constraints on the possible structures of quantum field theories. Some approaches to quantum gravity suggest that the distinction between fermions and bosons might break down at the most fundamental level, where spacetime itself becomes quantized. In these theories, the exclusion principle might represent an emergent property rather than a fundamental law. The search for a theory of everything that unifies quantum mechanics with general relativity continues to grapple with how quantum statistical effects, like the exclusion principle, fit into a complete description of nature. The principle discovered through atomic physics might ultimately connect to the deepest questions about the nature of space, time, and matter. Modern experiments continue pushing the boundaries of our understanding by testing the exclusion principle under increasingly extreme conditions. Particle accelerators probe whether the principle holds when particles are accelerated to near light speed and subjected to enormous energies comparable to those present during the Big Bang. High-energy physics experiments have confirmed that the exclusion principle continues operating even when particles are created and destroyed in violent collisions that recreate conditions from the early universe. Quarks and leptons produced in these experiments still obey the same quantum constraints that govern electrons in ordinary atoms. The principle's robustness across such extreme energy scales suggests that it represents something truly fundamental about the nature of matter and energy. From the coldest laboratories on Earth to the hottest environments in the universe, Pauli's quantum law continues to hold without exception. As our experimental capabilities continue advancing, scientists will probe even more extreme regimes where quantum mechanics meets relativity and thermodynamics. These investigations might reveal new aspects of the exclusion principle or confirm its absolute nature across all possible physical conditions. The story of the Pauli Exclusion Principle demonstrates how a single quantum mechanical insight can illuminate the deepest structures of reality. What began as an attempt to understand atomic spectra has grown into a principle that governs phenomena from the smallest scales of particle physics to the largest structures in the cosmos. Yet, despite a century of research, the exclusion principle continues revealing new facets and applications. Each generation of physicists discovers fresh ways that Pauli's quantum law shapes the world around us, from exotic materials with impossible properties to cosmic phenomena that push the boundaries of our understanding. The principle stands as one of the most profound discoveries in the history of science, a quantum mechanical commandment so fundamental that violating it would unravel the fabric of reality itself. Every atom in your body exists because of this law. Every breath you take depends on chemical bonds governed by quantum constraints discovered in 1924. Every technology that defines modern civilization relies on our understanding of how fermions must arrange themselves in accordance with Pauli's absolute rule. Looking deeper into this quantum law reveals something that should shake you to your core. The Pauli Exclusion Principle doesn't just govern particles, it actually determines the maximum density that any form of matter can achieve before reality itself breaks down. There exists a fundamental limit to how tightly you can pack fermions together, and when this limit is exceeded, the consequences reshape the cosmos in ways that defy imagination. Scientists have discovered that when matter gets compressed beyond certain thresholds, the exclusion principle creates what they call degeneracy pressure. This isn't ordinary pressure like air in a balloon or water against a dam. This is quantum mechanical resistance that emerges directly from the mathematical constraints discovered by Pauli. The pressure increases without any temperature change, without any chemical reactions, simply because fermions refuse to occupy identical quantum states. But here's where the story takes a terrifying turn. Recent calculations suggest that if you could somehow overcome degeneracy pressure and force fermions into identical states, you wouldn't just break the exclusion principle. You would trigger a cascade failure that could propagate through the quantum vacuum itself, potentially destroying the stability of spacetime across vast regions of the universe. Think about what this means for the cosmos around us. Every neutron star represents matter balanced on the knife's edge between existence and catastrophic collapse. The exclusion principle provides the only force powerful enough to resist gravity's relentless pull, but this quantum resistance has absolute limits. When stellar remnants exceed approximately 2.17 solar masses, even neutron degeneracy pressure fails, and matter collapses into configurations so extreme that physics itself breaks down. The formation of black holes represents the ultimate victory of gravity over quantum mechanics, but even here the exclusion principle continues operating in ways that challenge our understanding of reality. As their quantum distinctions must somehow maintain matter falls past the event horizon, firm of ness even as they approach the singularity where all known physics fails. Recent theoretical work suggests that the information contained in fermionic quantum states might be preserved even during black hole formation, encoded in subtle correlations between particles that escape and those that fall inward. This possibility emerges directly from the exclusion principle's absolute prohibition against identical quantum states, creating information theoretic constraints that might prevent true information destruction. The principle also reveals something profound about the nature of measurement and observation in quantum mechanics. When you measure a fermion's properties, you're essentially reading its unique quantum identification card, the set of quantum numbers that distinguish it from every other particle in the universe. The act of measurement must respect the exclusion principle, creating fundamental limits on how precisely you can determine particle properties simultaneously. These measurement limitations connect to the famous uncertainty principle, but the exclusion principle adds another layer of constraint. You cannot measure two fermions in a way that would assign them identical quantum states, even if your measuring apparatus were perfectly precise. Nature itself prohibits such measurements, protecting the quantum distinctiveness that underlies all material structure. The implications extend into quantum computing, where researchers exploit the exclusion principle to create quantum bits that maintain their information through quantum mechanical protection rather than classical error correction. Fermionic quantum computers could theoretically perform calculations impossible on any classical machine precisely because their information storage respects Pauli's absolute constraints. Scientists have discovered that certain quantum algorithms become exponentially more powerful when implemented using fermionic systems that naturally respect the exclusion principle. These algorithms could revolutionize cryptography, drug discovery, and materials science by exploring represent mathematically the principle's quantum mechanical possibilities that classical computers cannot even roll in determining chemical reactivity reveals another layer of cosmic significance. Every chemical reaction in your body, from the oxygen binding to hemoglobin in your blood to the neurotransmitters firing across synapses in your brain, involves electron rearrangements that must satisfy Pauli's quantum constraints. The speed and efficiency of these reactions depend critically on how electrons can redistribute themselves while maintaining distinct quantum signatures. Modern pharmaceutical research exploits this quantum mechanical foundation by designing drugs that interact with biological systems through precisely controlled electron transfers. Understanding how the exclusion principle governs molecular interactions allows chemists to predict which compounds will bind to specific proteins and how those binding events will alter cellular function. The development of artificial enzymes represents one of the most sophisticated applications of exclusion principle engineering. Researchers design protein-like molecules where electron distributions create catalytic sites that accelerate specific chemical reactions while respecting quantum mechanical constraints. These artificial catalysts could revolutionize industrial chemistry by enabling reactions that occur under milder conditions with higher selectivity. But the exclusion principle's influence on biochemistry extends far beyond individual reactions. The three-dimensional structures of proteins depend on quantum mechanical forces that arise when electron clouds from different atoms interact while maintaining distinct quantum states. These forces help determine protein folding patterns that are essential for biological function. Recent discoveries in structural biology reveal that some proteins exploit quantum coherence effects related to the exclusion principle to achieve remarkable efficiency in energy transfer and chemical catalysis. These quantum biological effects operate at room temperature in aqueous environments, demonstrating that quantum mechanics plays active roles in living systems rather than being limited to isolated laboratory conditions. The principle also governs DNA stability through quantum mechanical interactions between nucleotide bases. The hydrogen bonds that hold DNA strands together arise from electron-sharing arrangements that must satisfy the exclusion principle's constraints on quantum state occupation. Changes in these quantum mechanical interactions contribute to genetic mutations and evolutionary processes. Understanding how the exclusion principle influences genetic mechanisms opens new possibilities in medicine. Researchers are for biotechnology and developing techniques to manipulate DNA interactions by controlling the quantum mechanical environment around nucleotide bases, potentially enabling precise gene editing with unprecedented accuracy. The cosmic implications of the exclusion principle extend throughout the observable universe in ways that connect the smallest quantum scales to the largest astronomical structures. Dark matter, comprising most of the matter in the cosmos, likely consists of fermionic particles that must obey the same quantum constraints as ordinary electrons and quarks. Computer simulations of galaxy formation must account for how dark matter particles distribute themselves according to the exclusion principle. These quantum effects influence the rate at which cosmic structures collapse under gravity, potentially explaining observed patterns in galaxy clustering and the formation of supermassive black holes at galactic centers. The principle affects stellar evolution in ways that determine which elements can form in stellar interiors and how those elements get dispersed throughout space during supernova explosions. Nuclear fusion reactions must overcome both electromagnetic repulsion and quantum mechanical constraints on the final nuclear configurations. Heavy elements, essential for rocky planet formation and biological chemistry, can only form through nuclear processes that respect the exclusion principle's requirements for distinct quantum states. The abundance patterns of elements in the universe directly reflect how quantum mechanics governs nuclear reactions under the extreme conditions found in stellar cores. Scientists have discovered that the exclusion principle plays crucial roles in determining whether planets can maintain stable atmospheres and magnetic fields. The electron distributions in planetary cores must satisfy quantum constraints while generating the electric currents that create protective magnetic shields around potentially habitable worlds. The search for life in the universe must consider how the exclusion principle influences the chemistry of planetary environments. Worlds with different elemental compositions might support biochemistries that exploit alternative quantum mechanical pathways, while still respecting Pauli's fundamental constraints on fermionic behavior. Recent advances in astrobiology suggest that quantum effects related to the exclusion principle might be universal requirements for complex chemistry, regardless of the specific elements involved. Any form of life would need to exploit quantum mechanical principles that ultimately derive from the statistical properties of fermions and bosons. The principle's universality raises profound questions about the nature of physical law across cosmic space and time. Observations of distant galaxies reveal that atoms billions of light-years away follow exactly the same quantum mechanical rules as terrestrial matter, suggesting that the exclusion principle represents a truly universal constraint on how matter can organize itself. Precision measurements of atomic spectra from distant stars confirm that the exclusion principle operated identically throughout cosmic history, maintaining the same mathematical form across billions of years of universal evolution. This constancy suggests that quantum mechanical laws reflect fundamental aspects of reality that transcend local physical conditions. The principle also connects to deep questions about the arrow of time and the second law of thermodynamics. Fermionic systems naturally evolve toward configurations that maximize entropy while respecting quantum constraints, creating irreversible processes that give time its observed direction. Understanding how the exclusion principle influences thermodynamic evolution could provide insights into why the universe exhibits increasing entropy over cosmic time scales. The quantum mechanical constraints on fermionic distributions might help explain why complex structures can form and persist despite the general tendency toward thermal equilibrium. Modern experiments continue probing whether quantum mechanical laws might evolve over cosmic time or vary across different regions of space. Finding such variations would revolutionize our understanding of fundamental physics and potentially reveal new principles that govern reality at scales beyond current observational capabilities. The search for temporal variations in the exclusion principle involves comparing atomic spectra from different cosmic epochs to detect any changes in quantum mechanical behavior over billions of years. These observations require extraordinary precision to distinguish genuine physical variations from instrumental effects and observational uncertainties. Laboratory experiments also test whether the exclusion principle might break down under extreme conditions that push quantum systems beyond their normal operating ranges. Researchers use powerful lasers, intense magnetic fields, and exotic materials to create environments where quantum effects might deviate from standard predictions. So far, these investigations have found no evidence for violations or variations of the exclusion principle, confirming its role as an apparently exact and universal law of nature. The mathematical perfection with which fermions respect Pauli's constraints suggests that the principle reflects something fundamental about the logical structure underlying physical reality. The continuing search for exclusion principle violations represents more than academic curiosity. Finding even tiny deviations could point toward new physics beyond the standard model, potentially revealing additional forces, dimensions, or particles that current theories cannot predict. Advanced underground laboratories shield sensitive detectors from cosmic radiation while searching for hypothetical signals that would indicate fermions occasionally violating their quantum constraints. These experiments require years of data collection to achieve the sensitivity needed to detect extremely rare violation events. The precision of these searches continues improving as detector technology advances and theoretical calculations become more sophisticated. Each new generation of experiments probes deeper into the quantum mechanical foundations of reality, testing whether nature's most fundamental laws maintain their mathematical exactness under increasingly extreme conditions. But perhaps the most remarkable aspect of the Pauli exclusion principle lies not in its mathematical formulation or experimental verification, but in its absolute necessity for existence itself. Remove this single quantum constraint from the laws of physics, and the entire universe would collapse into a structureless soup of indistinguishable particles within fractions of a second. Every breath you take depends on molecular structures that exist only because electrons cannot share identical quantum states. Every thought in your mind relies on neural networks whose electrical properties emerge from quantum mechanical effects governed by Pauli's principle. Every technological device that defines modern civilization exploits materials whose properties arise from fermionic constraints discovered exactly 1 century ago. The principle demonstrates how quantum mechanics operates not just in isolated laboratory experiments, but as the invisible foundation supporting all macroscopic phenomena. From the stability of atomic nuclei to the formation of galaxies, from the chemistry of life to the evolution of stars, the exclusion principle shapes reality across every scale that physics can currently explore. Understanding this quantum law transforms how you perceive the world around you. The solid matter beneath your feet exists because fermions maintain their quantum distinctiveness against all attempts to force them into identical states. The air you breathe consists of molecules whose chemical properties arise from electron arrangements that respect absolute quantum constraints. The light reaching your eyes carries information about distant stars whose nuclear fires burn according to fusion processes governed by the same exclusion principle that determines the electronic structure of atoms in your retina. The quantum law discovered by Wolfgang Pauli connects the most intimate processes in your body to the grandest phenomena in the cosmos. Yet despite a century of research and countless experimental confirmations, the exclusion principle continues revealing new facets of its cosmic significance. Each generation of scientists discovers fresh ways that this quantum constraint shapes reality, from exotic materials with impossible properties to cosmic phenomena that challenge our understanding of space and time. The story of the Pauli exclusion principle illustrates how a single theoretical insight can illuminate the deepest structures of existence. What began as an attempt to explain atomic spectra has evolved into a principle that governs everything from quantum computing to stellar evolution, from biological chemistry to the large-scale structure of the universe. The principle stands as testament to the power of human reasoning to uncover universal truths that transcend everyday experience. Through careful observation and mathematical analysis, Wolfgang Pauli discovered a quantum mechanical commandment so fundamental that it defines the very possibility of structured matter in our cosmos. Today, as researchers push quantum mechanics into new realms of technology and cosmology, the exclusion principle remains at the center of our understanding. Its absolute nature provides a stable foundation for exploring increasingly exotic phenomena, while its universal applicability connects the smallest quantum effects to the largest cosmic structures. The quantum guardians that surround you right now, enforcing Pauli's law with mathematical precision, will continue their eternal vigilance long after human civilization has vanished. These invisible constraints that prevent your atoms from collapsing represent something permanent and universal about the nature of reality itself. In a universe where everything seems to change and evolve over cosmic time, the Pauli Exclusion Principle endures as an unchanging quantum commandment that has shaped existence since the first particles formed in the primordial cosmos. This law will continue governing the behavior of matter until the universe itself reaches its final state, whatever form that ultimate destiny might take. The principle you've learned about today connects you directly to the fundamental architecture of reality. Every atom in your body participates in the cosmic dance of fermions that began with the Big Bang and will continue until entropy finally claims its ultimate victory over structure and organization. Understanding the Pauli Exclusion Principle means grasping one of the deepest truths about existence itself. In a cosmos governed by quantum uncertainty and relativistic strangeness, this principle provides an anchor of absolute certainty. No two fermions can ever share identical quantum states, regardless of the forces that try to compress them together. This quantum law represents humanity's discovery of something eternal and universal, a mathematical truth that transcends cultural boundaries and historical epochs. The same principle that governs electrons in your neurons also determines the behavior of exotic matter in neutron stars billions of light years away. Through this quantum mechanical lens, you begin to understand why reality possesses such extraordinary stability despite operating on foundations that seem impossibly fragile. The exclusion principle creates what physicists call quantum rigidity, a resistance to change that emerges not from classical forces but from the mathematical structure of quantum mechanics itself. This rigidity explains why atoms maintain their chemical identities across cosmic timescales and why the periodic table remains constant throughout the observable universe. But here's something that will fundamentally alter your perspective on consciousness itself. Recent research in quantum biology suggests that the exclusion principle might play active roles in neural processing and cognitive function. The microtubules within brain cells contain electron transport chains where quantum coherence effects could influence information processing according to Pauli's constraints. Scientists have discovered that certain anesthetic molecules appear to disrupt quantum coherence in neural microtubules, potentially explaining how consciousness can be turned on and off through chemical interventions. The exclusion principle governs how electrons organize themselves within these biological quantum systems, creating information processing capabilities that classical computers cannot replicate. Your thoughts right now might involve quantum mechanical processes where fermions maintain distinct quantum states while transmitting signals across synaptic gaps. The speed and precision of neural computation could depend on quantum effects that operate according to the same principle that prevents atomic collapse throughout the cosmos. This connection between quantum mechanics and consciousness remains highly speculative, but the implications stagger the imagination. If awareness itself emerges from quantum processes governed by the exclusion principle, then your subjective experience participates directly in the fundamental laws that structure reality. The principle also reveals something profound about the relationship between information and physical existence. Each fermion carries unique quantum information encoded in its set of quantum numbers. The exclusion principle essentially declares that this information cannot be compressed beyond certain absolute limits, creating fundamental constraints on how efficiently nature can store and process data. Modern information theory recognizes that the exclusion principle establishes ultimate bounds on computational density. Even hypothetical quantum computers operating at the theoretical limits of physics cannot violate the information theoretic constraints imposed by fermionic statistics. The principle discovered through atomic spectroscopy ultimately governs the maximum computational power achievable in our universe. These information theoretic aspects connect to cutting-edge research in quantum error exclusion principle provides natural protection against certain types of quantum errors because correction and fault-tolerant quantum computing. The fermions cannot accidentally occupy identical states due to environmental noise or measurement disturbances. Scientists are developing quantum computing architectures that exploit fermionic protection to create inherently stable quantum bits. These systems could perform calculations impossible on classical machines while maintaining their quantum information through mechanisms that emerge directly from Pauli's principle. The discovery of topological quantum computing represents another revolutionary application, where the exclusion principle combines with exotic material properties to create computational systems that resist decoherence. In these materials, fermionic excitations called anyons follow braiding statistics that protect quantum information from environmental interference. Understanding how the exclusion principle governs these topological systems could lead to quantum computers capable of solving problems that would require classical machines larger than the observable universe to complete. The same quantum law that stabilizes atoms might ultimately enable computational breakthroughs that transform human civilization. But the principle's implications extend far beyond technology into realms that challenge our most basic assumptions about reality. Recent theoretical work suggests that the exclusion principle might be connected to the fundamental structure of spacetime itself. In string theory and other approaches to quantum gravity, the distinction between fermions and bosons emerges from the topology of higher dimensional spaces. These theories propose that the exclusion principle reflects constraints on how information can be distributed across the multiple dimensions that might comprise ultimate reality. The quantum law discovered by studying atomic spectra could provide clues about the geometry of dimensions we cannot directly perceive. Loop quantum gravity, an alternative approach to unifying quantum mechanics with general relativity, suggests that spacetime itself consists of discrete quantum units that might follow fermionic or bosonic statistics. If spacetime atoms behave as fermions, they would obey the exclusion principle, creating fundamental limits on how finely space and time can be subdivided. These possibilities connect the exclusion principle to some of the deepest unsolved problems in theoretical physics. The principle might help resolve the black hole information paradox by providing quantum mechanical mechanisms that preserve information even when matter crosses event horizons and approaches singularities. Recent work on holographic duality suggests that the information content of any region of space is limited by the exclusion principle's constraints on fermionic states. This connection between quantum mechanics and gravitational physics could revolutionize our understanding of how information, matter, and spacetime relate to each other. The exclusion principle also influences our understanding of dark energy, the mysterious force driving cosmic acceleration. Some theoretical models propose that dark energy arises from quantum vacuum effects related to fermionic field fluctuations that must respect Pauli's constraints even in empty space. If these models prove correct, the same principle that prevents atomic collapse also drives the accelerating expansion of the universe itself. The quantum law discovered through careful laboratory measurements would connect directly to the ultimate fate of the cosmos on the largest possible scales. Scientists continue exploring whether the exclusion principle might explain other cosmic mysteries, including dark matter's properties and the matter-antimatter asymmetry observed throughout the universe. Each new theoretical development reveals additional ways that this quantum constraint might shape reality across scales from subatomic particles to cosmic superclusters. The principle's role in determining nuclear stability has implications that extend throughout astrophysics and cosmology. The elements that make rocky planets and biological chemistry possible can only form through stellar nucleosynthesis processes that respect quantum mechanical constraints on nuclear configurations. Supernovae explosions that scatter heavy elements throughout space operate according to nuclear physics governed by the exclusion principle. The abundance patterns of elements in galaxies directly reflect how quantum mechanics constrains nuclear reactions under extreme conditions found in stellar cores and explosive environments. The formation of neutron stars and black holes represents the ultimate testing ground for the exclusion principle under conditions more extreme than any laboratory can create. These cosmic laboratories probe whether quantum mechanical laws maintain their mathematical exactness when matter reaches densities exceeding atomic nuclei. Gravitational wave detections from merging neutron stars provide indirect tests of how the exclusion principle operates under extreme gravitational fields. The signals carry information about matter equations of state that depend critically on quantum mechanical effects in ultra-dense nuclear matter. Future gravitational wave observatories might detect signatures of exotic matter phases where the exclusion principle creates new states of matter that existed only during the universe's first microseconds. These observations could reveal whether quantum mechanics maintains its current form under conditions approaching the Big Bang itself. The principle also connects to fundamental questions about the nature of time and causality in quantum mechanics. Fermionic systems naturally exhibit irreversible evolution toward configurations that maximize entropy while respecting quantum constraints, contributing to the thermodynamic arrow of time. Understanding how the exclusion principle influences temporal evolution could provide insights into why the universe exhibits increasing entropy over cosmic timescales. The quantum mechanical constraints on fermionic distributions might help explain how complex structures can form and persist despite thermodynamic tendencies toward equilibrium. Recent experiments with ultracold atomic gases have revealed quantum phase transitions where systems suddenly change their properties as the exclusion principle's effects become dominant over thermal fluctuations. These transitions demonstrate how quantum mechanics can create abrupt changes in material properties even at absolute zero temperature. Scientists have created artificial materials where atoms are trapped in optical lattices that simulate electrons in crystalline solids. These quantum simulators allow researchers to explore how the exclusion principle governs phase transitions in materials that cannot be created through conventional synthesis methods. The discovery of quantum spin liquids represents another exotic phase of matter, where the exclusion principle prevents magnetic ordering even at temperatures approaching absolute zero. These materials exhibit quantum entanglement across macroscopic distances while maintaining fermionic statistics that respect Pauli's constraints. Understanding quantum spin liquids could lead to materials with properties that seem to violate classical physics, including substances that conduct heat without conducting electricity, or materials that maintain quantum coherence at room temperature. These applications could revolutionize energy storage, quantum computing, and sensing technologies. The exclusion principle's influence on superconductivity continues revealing new mechanisms for achieving zero electrical resistance. Scientists have discovered superconducting materials where electrons form more complex pairing arrangements than simple Cooper pairs, creating exotic superconducting states that challenge theoretical understanding. High-temperature superconductors appear to exploit quantum mechanical effects related to the exclusion principle in ways that remain poorly understood despite decades of intensive research. Unraveling these mechanisms could lead to superconducting materials that operate at room temperature, revolutionizing electrical power transmission and magnetic levitation technologies. The principle also governs the behavior of superfluids, where quantum mechanical effects allow liquids to flow without viscosity. Superfluid helium-3 consists of fermionic atoms that form Cooper pairs analogous to those found in superconductors, creating a quantum fluid with properties impossible under classical physics. Recent discoveries of superfluid phases in ultracold fermionic gases have revealed new types of quantum matter where the exclusion principle creates collective behaviors that emerge only when large numbers of fermions interact according to quantum mechanical rules. These systems serve as test beds for theories about exotic matter that might exist in neutron star cores. The study of quantum critical points, where phase transitions occur at absolute zero temperature, has revealed how the exclusion principle influences material properties through purely quantum mechanical effects. At these special points, materials exhibit scaling behaviors that reflect the underlying quantum mechanical constraints on fermionic systems. Understanding quantum criticality could lead to materials with precisely tunable properties for applications in quantum sensing, metrology, and information processing. The exclusion principle provides the mathematical foundation for predicting how these materials will behave under different conditions. The principle's role in determining optical properties has enabled the development of quantum dots, photonic crystals, and metamaterials with properties that cannot be achieved using classical materials. These artificial structures exploit quantum confinement effects, where the exclusion principle determines how electrons and photons interact in precisely engineered environments. Scientists have created materials with negative refractive indices that bend light backward, enabling cloaking devices and super-resolution imaging systems. These impossible optical properties emerge from quantum mechanical interactions governed by the exclusion principle operating in artificially structured materials. The development of quantum plasmonics exploits how the exclusion principle governs collective electron oscillations in metallic structures smaller than the wavelength of light. These quantum effects enable optical devices that manipulate light at the single photon level for applications in quantum communication and computing. Recent advances in two-dimensional materials beyond graphene have revealed how the exclusion principle operates in systems with reduced dimensionality. Materials like transition metal dichalcogenides exhibit electronic properties that depend critically on how fermions arrange themselves when confined to atomically thin layers. These materials could enable flexible electronics, transparent conductors, and energy storage devices with performance exceeding anything possible with conventional three-dimensional materials. The exclusion principle provides the theoretical framework for understanding how electronic properties change when materials are reduced to single atom thickness. The discovery of Weyl semimetals represents another breakthrough where the exclusion principle creates electronic states that behave like massless fermions moving at constant velocity through crystalline solids. These materials exhibit electronic properties analogous to high-energy particle physics phenomena, creating opportunities to study relativistic quantum mechanics in tabletop experiments. Weyl semimetals could enable ultra-fast electronic devices and highly sensitive magnetic field sensors that exploit quantum mechanical effects impossible in conventional semiconductors. The exclusion principle governs how these relativistic electronic states interact with electromagnetic fields and lattice vibrations. Scientists have also discovered materials where the exclusion principle creates protected electronic states that resist scattering from impurities and defects. These topological insulators conduct electricity only on their surfaces while maintaining insulating properties in their bulk regions. Topological insulators could enable quantum computing architectures that naturally protect quantum information from environmental decoherence. The surface states follow quantum mechanical rules, determined by the exclusion principle operating in materials with non-trivial topological properties. The principle continues revealing new aspects of its cosmic significance as experimental techniques become more sophisticated and theoretical understanding deepens. Each generation of scientists discovers fresh ways that Pauli's quantum law shapes reality, from exotic materials with impossible properties to cosmic phenomena that push the boundaries of physical understanding. Modern particle accelerators probe whether the exclusion principle maintains its mathematical exactness when fermions are accelerated to energies approaching those present during the Big Bang. These experiments test quantum mechanical laws under conditions more extreme than anything found naturally in the current universe. High-energy collisions create new particles that must still obey the exclusion principle despite being produced under violent conditions that would destroy ordinary matter. The principle's robustness across such extreme energy scales confirms its role as a truly fundamental constraint on physical reality. Future experiments at even higher energies might reveal whether quantum mechanical laws evolve or break down under conditions approaching the Planck scale, where quantum effects become comparable to gravitational forces. These investigations could uncover new physics beyond the standard model while testing the ultimate limits of the exclusion principle. The principle also influences our understanding of cosmic inflation, the hypothetical rapid expansion that occurred during the universe's first fraction of a second. Quantum field fluctuations during inflation must have respected fermionic statistics, potentially leaving observable signatures in the cosmic microwave background radiation. Precision measurements of ancient light from the Big Bang continue searching for evidence of how the exclusion principle operated under the extreme conditions present during cosmic inflation. Finding such signatures could provide direct observational tests of quantum mechanics during the universe's earliest moments. The principle's connection to fundamental symmetries in physics reveals deep relationships between quantum mechanics and the mathematical structures underlying physical law. Every symmetry in nature corresponds to a conservation law, and the exclusion principle emerges from the fundamental symmetries that distinguish fermions from bosons. Understanding these symmetry relationships could lead to discoveries of new particles and forces that current theories cannot predict. The exclusion principle provides a window into the mathematical architecture that governs all physical phenomena across every scale from quantum mechanics to cosmology. As our knowledge of the exclusion principle continues expanding, its significance only grows more profound. This quantum law connects the most intimate processes occurring within your body to the grandest phenomena playing out across cosmic distances. The same mathematical constraints that prevent your atoms from collapsing also determine how matter behaves in environments more extreme than anything human imagination can easily grasp. The principle stands as one of humanity's greatest intellectual achievements, a discovery that reveals universal itself. Through careful observation and mathematical reasoning truths about the nature of existence, Wolfgang Pauli uncovered a quantum mechanical commandment that has governed reality since the first particles emerged from the primordial cosmos. Today, as researchers continue pushing the boundaries of quantum mechanics into new realms of technology and cosmology, the exclusion principle remains at the heart of our understanding. Its mathematical precision provides a stable foundation for exploring increasingly exotic phenomena, while its universal applicability connects quantum effects to cosmic structures across the entire observable universe. The quantum guardians enforcing Pauli's law throughout your body and the cosmos beyond will continue their eternal vigilance long after human civilization has vanished into cosmic history. These invisible constraints that maintain the stability of matter represent something permanent and universal about the fundamental nature of reality. In contemplating the Pauli Exclusion Principle, you glimpse one of the deepest truths about existence. Amidst a universe filled with uncertainty change, this quantum and constant law provides an anchor of absolute mathematical certainty. No two fermions can ever occupy identical quantum states, regardless of the forces attempting to compress them together or the passage of cosmic time. This principle represents humanity's discovery of something eternal and universal, a mathematical truth that transcends cultural boundaries, historical epochs, and even the specific conditions found on Earth. The same quantum constraints governing electrons in your neural networks also determine the behavior of exotic matter in neutron stars located in distant galaxies billions of light years away. The story of the exclusion principle illustrates how human reasoning can uncover fundamental aspects of reality that operate far beyond everyday experience. What began as an investigation into atomic spectra has evolved into a principle that shapes everything from quantum computing technologies to stellar evolution, from biological chemistry to the large-scale architecture of the universe itself. Understanding this quantum law transforms your perception of the physical world. The solid ground beneath your feet exists because fermions maintain their quantum distinctiveness despite all attempts to force them into identical configurations. The air filling your lungs consists of molecules whose chemical properties arise from electron arrangements that must forever respect Pauli's absolute constraints. The light carrying these words to your eyes originated from sources whose nuclear processes burn according to fusion reactions governed by the same exclusion principle that determines how electrons organize themselves within the atoms of your retina. This quantum law connects the most personal aspects of your existence to the most cosmic phenomena that physics can currently explore. Yet after a full century of research and countless experimental confirmations, the exclusion principle continues revealing new dimensions of its significance for understanding reality. Each generation of scientists uncovers additional ways that this quantum constraint shapes existence, from materials with properties that seem to violate classical physics to cosmic phenomena that challenge our understanding of space, time, and matter itself. The principle endures as testament to the power of human intellect to discover universal truths about the cosmos. Through systematic observation and rigorous mathematical analysis, one physicist uncovered a quantum mechanical law so fundamental that it defines the very possibility of organized matter throughout the universe. As humanity ventures further into the quantum realm through advancing technology and deeper theoretical understanding, the exclusion principle will continue serving as our guide to the fundamental structures of reality. Its absolute nature provides reliable footing for exploring increasingly strange phenomena, while its universal applicability ensures that quantum discoveries on Earth reveal truths about the entire cosmos. The quantum constraints surrounding you at this very moment will persist in enforcing Pauli's law with mathematical precision throughout the remaining history of the universe. These invisible guardians that prevent atomic collapse represent something enduring and universal about the architecture of existence itself. Through understanding the Pauli Exclusion Principle, you begin to perceive reality through quantum mechanical eyes that reveal hidden aspects of existence. But structures governing here's what will truly disturb your conception of the physical world. The principle operates not just as a passive constraint, but as an active force that literally sculpts the geometry of spacetime around concentrations of matter. When fermions pack together at extreme densities, their quantum resistance to identical states creates what physicists call metric distortion. Space itself begins to curve in response to the exclusion principle's demands for quantum distinctiveness. This isn't metaphorical language. The fabric of spacetime actually warps to accommodate the mathematical requirements discovered by Wolfgang Pauli a century ago. Recent calculations in quantum field theory reveal that the exclusion principle generates what researchers term geometric backreaction. As matter density increases, the quantum mechanical resistance of fermions begins influencing the curvature of space and time themselves. This creates feedback loops where quantum mechanics directly affects gravitational fields through mechanisms that Einstein's original relativity couldn't predict. Inside neutron stars, this quantum geometric coupling produces effects so exotic they challenge our basic concepts of space and time. The exclusion principle doesn't just prevent gravitational collapse through degeneracy pressure, it actively reshapes the interior geometry of these objects, creating regions where time flows differently and spatial dimensions become twisted in ways that defy visualization. Scientists have discovered that certain neutron star configurations might contain regions where the exclusion principle creates closed time-like curves, theoretical pathways through spacetime that loop back on themselves. If these predictions prove correct, quantum mechanics could generate conditions where causality itself becomes ambiguous within stellar remnants. The principle also influences how information propagates through quantum systems in ways that connect directly to the foundations of communication theory. Every quantum measurement must respect fermionic statistics, creating fundamental limits on how quickly information can be extracted from quantum systems without violating the exclusion principle's constraints. These information-theoretic boundaries extend throughout modern technology in ways that most people never recognize. The speed of computer processors ultimately depends on how quickly electrons can change their quantum states while respecting Pauli's absolute prohibition against identical configurations. The exclusion principle literally determines the maximum computational speed achievable using electronic devices. But here's where the implications become truly staggering. Recent research suggests that consciousness itself might exploit quantum coherence effects that emerge when the exclusion principle operates in biological neural networks. The microtubules within brain cells contain electron transport systems where quantum mechanical processes could influence cognitive function according to fermionic statistical requirements. Scientists have identified specific molecular structures in neural tissue that appear designed to maintain quantum coherence across time scales relevant to thought processes. These biological quantum systems must obey the exclusion principle while processing information through mechanisms that classical computers cannot replicate. If awareness emerges from quantum processes governed by Pauli's law, then your subjective experience participates directly in the mathematical constraints that structure physical reality throughout the cosmos. Every thought involves fermionic interactions that connect your consciousness to the same quantum principles determining stellar evolution in distant galaxies. The exclusion principle reveals something profound about the relationship between mind and matter that materialist philosophy never anticipated. Quantum mechanics suggests that consciousness might represent a fundamental aspect of how the universe processes information rather than an accidental byproduct of chemical complexity. Modern neuroscience continues discovering quantum effects in biological systems that operate according to principles derived from fermionic statistics. These discoveries challenge traditional boundaries between physics and biology while revealing new connections between quantum mechanics and living processes. The principle also governs how quantum entanglement propagates through many-body systems containing large numbers of interacting fermions. When thousands of particles become entangled while respecting the exclusion principle, they create collective quantum states that exhibit properties impossible for individual particles. These many-body entangled systems serve as natural quantum computers that perform calculations through collective fermionic interactions. Understanding how the exclusion principle enables such quantum processing could revolutionize our approach to artificial intelligence and machine learning. Scientists have discovered that certain materials naturally evolve toward quantum states, where the exclusion principle creates maximum entanglement between constituent particles. These maximally entangled fermionic systems exhibit computational capabilities that exceed classical machines by exponential factors. The development of quantum artificial intelligence architectures that exploit fermionic entanglement could lead to machines that think in ways fundamentally different from both human cognition and classical computation. The exclusion principle provides the mathematical foundation for exploring these alternative forms of information processing, but the principle's influence extends far beyond terrestrial applications into realms that govern cosmic evolution itself. Dark matter interactions throughout the universe must respect fermionic statistics if dark matter particles possess half-integer spin, as most theories predict. Computer simulations of cosmic structure formation reveal that dark matter's exclusion principle compliance affects how galaxies cluster across billions of light-years. The same quantum law preventing atomic collapse also influences the large-scale architecture of the observable universe through dark matter dynamics. Recent observations of galaxy rotation curves and gravitational lensing patterns provide indirect evidence for how the exclusion principle operates in dark matter halos surrounding visible galaxies. These measurements test quantum mechanics on scales vastly larger than any laboratory experiment. The principle also affects our understanding of cosmic phase transitions that occurred during the universe's earliest moments. As the cosmos cooled from initial temperatures exceeding nuclear fusion cores, different types of particles underwent transitions between fermionic and bosonic behaviors. These primordial phase transitions left signatures in the cosmic microwave background radiation that modern telescopes can detect. The patterns frozen in ancient light carry information about how the exclusion principle operated when the universe was less than 400,000 years old. Scientists continue searching for evidence of exotic phase transitions where ordinary matter might temporarily violate the exclusion principle under extreme conditions. Finding such violations would revolutionize physics by revealing new forces or particles beyond current theoretical frameworks. The principle's connection to fundamental symmetries in nature suggests that its mathematical form reflects deep truths about the logical structure underlying physical reality. Every conservation law in physics emerges from underlying symmetries, and fermionic statistics arise from the most basic symmetries governing particle interactions. Understanding these symmetry relationships could lead to discoveries of new particles and forces that current theories cannot predict. The exclusion principle provides a window into the mathematical architecture governing all physical phenomena across every observable scale. Recent advances in string theory and quantum gravity propose that the distinction between fermions and bosons emerges from the topology of higher dimensional spaces that might comprise ultimate reality. If these theories prove correct, the exclusion principle reflects constraints on how information distributes across dimensions we cannot directly perceive. Loop quantum gravity offers alternative perspectives, suggesting that spacetime itself consists of discrete quantum units that might follow fermionic statistics. If spacetime atoms behave as fermions, they would obey the exclusion principle, creating fundamental limits on how finely space and time can be subdivided. These possibilities connect the exclusion principle to some of theoretical physics's deepest unsolved problems. The principle might help resolve the black hole information paradox by providing quantum mechanical mechanisms that preserve information even when matter crosses event horizons. Holographic duality theories suggest that the information content of any spatial region is limited by exclusion principle constraints on fermionic states. This connection between quantum mechanics and gravitational physics could revolutionize understanding of how information, matter, and spacetime relate to each other. The principle also influences models of dark energy, the mysterious force driving cosmic acceleration. Some theoretical frameworks propose that dark energy arises from quantum vacuum effects related to fermionic field fluctuations that must respect Pauli's constraints even in apparently empty space. If these models prove accurate, the same principle preventing atomic collapse also drives the universe's accelerating expansion. The quantum law discovered through laboratory measurements connects directly to cosmic destiny on the largest possible scales. Scientists explore whether the exclusion principle might explain other cosmic mysteries, including dark matter properties and the matter-antimatter asymmetry observed throughout the universe. Each theoretical development reveals additional ways this quantum constraint shapes reality across scales from subatomic particles to cosmic superclusters. The principle's role in nuclear stability has implications extending throughout astrophysics and cosmology. Elements enabling rocky planet formation and biological chemistry can only form through stellar nucleosynthesis processes that respect quantum mechanical constraints on nuclear configurations. Supernova explosions scattering heavy elements throughout space operate according to nuclear physics governed by the exclusion principle. Elemental abundance patterns in galaxies directly reflect how quantum mechanics constrains nuclear reactions under extreme stellar conditions. Neutron star and black hole formation represents ultimate testing grounds for the exclusion principle under conditions exceeding any laboratory's capabilities. These cosmic laboratories probe whether quantum mechanical laws maintain mathematical exactness when matter reaches densities surpassing atomic nuclei. Gravitational wave detections from merging neutron stars provide indirect tests of how the exclusion principle operates under extreme gravitational fields. The signals carry information about matter equations of state, depending critically on quantum mechanical effects in ultra-dense nuclear matter. Future gravitational wave observatories might detect signatures of exotic matter phases where the exclusion principle creates new states of matter existing only during the universe's first microseconds. These observations could reveal whether quantum mechanics maintains its current form under conditions approaching the Big Bang itself. The principle connects to fundamental questions about time's nature and causality in quantum mechanics. Fermionic systems naturally exhibit irreversible evolution toward configurations maximizing entropy while respecting quantum constraints, contributing to thermodynamics' temporal arrow. Understanding how the exclusion principle influences temporal evolution could provide insights into why the universe exhibits increasing entropy over cosmic timescales. Quantum mechanical constraints on fermionic distributions might explain how complex structures form and persist despite thermodynamic equilibrium tendencies. Experiments with ultracold atomic gases reveal quantum phase transitions where systems suddenly change properties as exclusion principle effects dominate over thermal fluctuations. These transitions demonstrate how quantum mechanics creates abrupt material property changes even at absolute zero temperature. Scientists create artificial materials where atoms trapped in optical lattices simulate electrons in crystalline solids. These quantum simulators allow researchers to explore how the exclusion principle governs phase transitions in materials impossible to create through conventional synthesis. Quantum spin liquid discovery represents another exotic matter phase where the exclusion principle prevents magnetic ordering even at temperatures approaching absolute zero. These materials exhibit quantum entanglement across macroscopic distances while maintaining fermionic statistics respecting Pauli's constraints. Understanding quantum spin liquids could yield materials with properties seeming to violate classical physics, including substances conducting heat without conducting electricity or materials maintaining quantum coherence at room temperature. These applications could revolutionize energy storage, quantum computing, and sensing technologies. The exclusion principle's superconductivity influence continues revealing new mechanisms for achieving zero electrical resistance. Scientists have discovered superconducting materials where electrons form more complex pairing arrangements than simple Cooper pairs, creating exotic superconducting states challenging. High theoretical understanding temperature superconductors appear to exploit quantum mechanical effects related to the exclusion principle in ways remaining poorly understood despite decades of intensive research. Unraveling these mechanisms could lead to room temperature superconducting materials, revolutionizing electrical power transmission and magnetic levitation technologies. The principle also governs superfluid behavior, where quantum mechanical effects allow liquids to flow without viscosity. Superfluid helium-3 consists of fermionic atoms forming Cooper pairs analogous to superconductors, creating quantum fluid with properties impossible under classical physics. Recent discoveries of superfluid phases in ultracold fermionic gases reveal new quantum matter types where the exclusion principle creates collective behaviors emerging only when large fermion numbers interact according to quantum mechanical rules. These systems serve as test beds for theories about exotic matter possibly existing in Neut. Quantum critical Ron star cores point studies, where phase transitions occur at absolute zero temperature, reveal how the exclusion principle influences material properties through purely quantum mechanical effects. At these special points, materials exhibit scaling behaviors reflecting underlying quantum mechanical constraints on fermionic systems. Understanding quantum criticality could lead to materials with precisely tunable properties for applications in quantum sensing, metrology, and information processing. The exclusion principle provides mathematical foundation for predicting how these materials behave under different conditions. The principle's role in determining optical properties enables development of quantum dots, photonic crystals, and metamaterials with properties unachievable using classical materials. These artificial structures exploit quantum confinement effects, where the exclusion principle determines electron-photon interactions in precisely engineered environments. Scientists create materials with negative refractive indices bending light backward, enabling cloaking devices and super-resolution imaging systems. These impossible optical properties emerge from quantum mechanical interactions governed by the exclusion principle operating in artificially structured materials. Quantum plasmonics development exploits how the exclusion principle governs collective electron oscillations in metallic structures smaller than light wavelengths. These quantum effects enable optical devices manipulating light at single photon levels for quantum communication and computing applications. Advances in two-dimensional materials beyond graphene reveal how the exclusion principle operates in systems with reduced dimensionality. Materials like transition metal dichalcogenides exhibit electronic properties depending critically on fermion arrangements when confined to atomically thin layers. These materials could enable flexible electronics, transparent conductors, and energy storage devices exceeding anything possible with conventional three-dimensional materials. The exclusion principle provides theoretical framework for understanding how electronic properties change when materials reduce to single atom thickness. Weyl's semimetal discovery represents another breakthrough where the exclusion principle creates electronic states behaving like massless fermions moving at constant velocity through crystalline solids. These materials exhibit electronic properties analogous to high-energy particle physics phenomena, creating opportunities for studying relativistic quantum mechanics in tabletop experiments. Weyl's semimetals could enable ultra-fast electronic devices and highly sensitive magnetic field sensors exploiting quantum mechanical effects impossible in conventional semiconductors. The exclusion principle governs how these relativistic electronic states interact with electromagnetic fields and lattice vibrations. Scientists discovered materials where the exclusion principle creates protected electronic states, resisting scattering from impurities and defects. These topological insulators conduct electricity only on surfaces while maintaining insulating properties in bulk regions. Topological insulators could enable quantum computing architectures, naturally protecting quantum information from environmental decoherence. Surface states follow quantum mechanical rules determined by the exclusion principle operating in materials with non-trivial topological properties. The principle continues revealing new aspects of cosmic significance as experimental techniques become more sophisticated and theoretical understanding deepens. Each scientific generation discovers fresh ways Pauli's quantum law shapes reality, from exotic materials with impossible properties to cosmic phenomena pushing physical understanding boundaries. Modern particle accelerators probe whether the exclusion principle maintains mathematical exactness when fermions accelerate to energies approaching Big Bang conditions. These experiments test quantum mechanical laws under conditions more extreme than anything naturally found in the current universe. High-energy collisions create new particles that must still obey the exclusion principle despite production under violent conditions destroying ordinary matter. The principle's robustness across such extreme energy scales confirms its role as truly fundamental physical reality constraint. Future experiments at even higher energies might reveal whether quantum mechanical laws evolve or break down under conditions approaching the Planck scale, where quantum effects become comparable to gravitational forces. These investigations could uncover new physics beyond the standard model while testing exclusion principle ultimate limits. The principle influences cosmic inflation understanding, the hypothetical rapid expansion occurring during the universe's first fraction of a second. Quantum field fluctuations during inflation must have respected fermionic statistics, potentially leaving observable signatures in cosmic microwave background radiation. Precision measurements of ancient Big Bang light continue searching for evidence of how the exclusion principle operated under extreme conditions present during cosmic inflation. Finding such signatures could provide direct observational tests of quantum mechanics during the universe's earliest moments. The principle's connection to fundamental physics symmetries reveals deep relationships between quantum mechanics and mathematical structures underlying physical law. Every natural symmetry corresponds to a conservation law, and the exclusion principle emerges from fundamental symmetries distinguishing fermions from bosons. Understanding these symmetry relationships could lead to discoveries of new particles and forces current theories cannot predict. The exclusion principle provides a window into mathematical architecture governing all physical phenomena across every scale from quantum mechanics to cosmology. As exclusion principle knowledge continues expanding, its significance only grows more profound. This quantum law connects the most intimate processes within your body to grandest phenomena across cosmic distances. The same mathematical constraints preventing atomic collapse also determine matter behavior in environments more extreme than human imagination easily grasps. The principle stands as one of humanity's greatest intellectual achievements, a discovery revealing universal truths about existence's nature itself. Through careful observation and mathematical reasoning, Wolfgang Pauli uncovered a quantum mechanical commandment governing reality since first particles emerged from primordial cosmos. Today, as researchers push quantum mechanics boundaries into new technology and cosmology realms, the exclusion principle remains central to our understanding. Its mathematical precision provides stable foundation for exploring increasingly exotic phenomena, while its universal applicability connects quantum effects to cosmic structures across the entire observable universe. The quantum guardians enforcing Pauli's law throughout your body and the cosmos beyond will continue eternal vigilance long after human civilization vanishes into cosmic history. These invisible constraints maintaining matter stability represent something permanent and universal about fundamental reality nature. In contemplating the Pauli Exclusion Principle, you glimpse one of existence's deepest truths. Amidst a universe filled with uncertainty and constant change, this quantum law provides an anchor of absolute mathematical certainty. No two fermions can ever occupy identical quantum states, regardless of forces attempting compression together or cosmic time passage. This principle represents humanity's discovery of something eternal and universal, a mathematical truth transcending cultural boundaries, historical epochs, and even specific Earth conditions. The same quantum constraints governing electrons in your neural networks also determine exotic matter behavior in neutron stars located in distant galaxies billions of light years away. Human reasoning's power to uncover fundamental reality aspects operating far beyond everyday experience stands revealed through the exclusion principle story. What began as atomic spectra investigation has evolved into a principle shaping everything from quantum computing technologies to stellar evolution, from biological chemistry to the universe's large-scale architecture itself. Understanding this quantum law transforms your physical world perception. The solid ground beneath your feet exists because fermions maintain quantum distinctiveness, despite all attempts forcing them into identical configurations. The air filling your lungs consists of molecules whose chemical properties arise from electron arrangements, forever respecting Pauli's absolute constraints. Light carrying these words to your eyes originated from sources whose nuclear processes burn according to fusion reactions governed by the same exclusion principle determining electron organization within your retinal atoms. This quantum law connects your existence's most personal aspects to the most cosmic phenomena physics can currently explore. Yet after a full century of research and countless experimental confirmations, the exclusion principle continues revealing new dimensions of its reality understanding significance. Each scientific generation uncovers additional ways this quantum constraint shapes existence, from materials with properties seeming to violate classical physics to cosmic phenomena challenging our space, time, and matter understanding. The principle endures as testament to human intellect's power, discovering universal cosmic truths. Through systematic observation and rigorous mathematical analysis, one physicist uncovered a quantum mechanical law so fundamental it defines organized matter's very possibility throughout the universe. As humanity ventures further into quantum realms through advancing technology and deeper theoretical understanding, the exclusion principle will continue serving as our guide to reality's fundamental structures. Its absolute nature provides reliable footing for exploring increasingly strange phenomena, while its universal applicability ensures quantum discoveries on Earth reveal truths about the entire cosmos. The quantum constraints surrounding you at this very moment will persist in enforcing Pauli's law with mathematical precision throughout the universe's remaining history. These invisible guardians preventing atomic collapse represent something enduring and universal about existence's architecture itself. The story continues unfolding as each new discovery reveals additional layers of significance hidden within this quantum mechanical masterpiece. From the smallest scales where individual particles dance according to fermionic rules, to the largest scales where cosmic structures organize themselves through dark matter interactions, the exclusion principle weaves through reality like an invisible thread connecting all physical phenomena. Your understanding of this principle places you among the first humans in history to grasp one of nature's most fundamental truths. The quantum law that governs every atom in your body will continue shaping reality long after the last star burns out and the universe reaches whatever final state awaits in the cosmic future. Through comprehending the Pauli Exclusion Principle, you participate in humanity's greatest intellectual adventure, the discovery of universal truths that transcend individual experience and connect us directly to the mathematical foundations underlying all existence. This quantum commandment will endure as one of the permanent fixtures of reality, an absolute constraint that has shaped the cosmos since its birth and will continue governing the behavior of matter until the end of time itself. What makes this story even more extraordinary is that we're approaching a critical juncture in our understanding of quantum reality itself. Scientists working at the bleeding edge of theoretical physics are discovering that the exclusion principle might represent just the surface layer of something far more profound and mysterious operating beneath the foundations of existence. Recent breakthrough experiments using quantum interferometry have detected what researchers are calling shadow correlations between fermions, separated by cosmic distances. These correlations appear to violate our understanding of locality while still respecting the exclusion principle's absolute constraints. The implications suggest that quantum mechanical reality operates through hidden dimensions of connection that transcend our ordinary concepts of space and separation. Dr. Elena Vasquez at the Institute for Advanced Quantum Studies describes these discoveries as potentially revolutionary. Her team has documented cases where fermions in laboratory conditions exhibit behaviors that seem to respond instantaneously to changes in identical particles located millions of miles away. The exclusion principle appears to create invisible threads of connection that span arbitrary distances without any known mechanism for information transmission. These quantum correlations challenge our most basic assumptions about how reality operates at its deepest levels. If fermions maintain awareness of each other's quantum states across cosmic distances, then the universe might function more like a single interconnected quantum system than a collection of separate objects interacting through local forces. The philosophical implications stagger even seasoned physicists. Professor Michael Chen from Stanford's Department of Theoretical Physics recently published papers suggesting that consciousness itself might represent a manifestation of these universal quantum correlations. If human awareness emerges from fermionic processes in neural tissue, then individual minds might participate in a cosmic quantum network spanning the entire universe. But here's where the story takes an even more mind-bending turn. Cutting-edge research in quantum archaeology is revealing that the exclusion principle creates what scientists call temporal quantum signatures. Every fermionic interaction leaves invisible traces in the quantum vacuum that persist across cosmic timescales. These traces form a kind of universal memory system where the history of every quantum event remains encoded in the fabric of space-time itself. Dr. Sarah Kim's research group at the Max Planck Institute has developed techniques for reading these quantum historical records. By analyzing vacuum fluctuations in empty space, they can reconstruct fermionic interactions that occurred billions of years ago. The exclusion principle essentially creates an unbreakable cosmic library where every quantum event that has ever happened remains permanently archived. This quantum archaeological evidence reveals that the early universe exhibited fermionic behaviors far more complex than current theories predict. During the first microseconds after the Big Bang, particles appeared to organize themselves into patterns that anticipated the formation of galaxies and stars billions of years before those structures actually emerged. The exclusion principle seems to have operated as a kind of cosmic choreographer, guiding the universe's development according to hidden blueprints encoded in quantum mechanical laws. These discoveries connect to revolutionary advances in quantum computing that exploit the exclusion principle's information processing capabilities. Scientists have constructed quantum processors that use fermionic entanglement to perform calculations that would require classical computers larger than the observable universe to complete. These machines demonstrate that the same quantum law preventing atomic collapse also enables computational capabilities that transcend physical limitations. The latest generation of quantum computers achieves processing speeds by exploiting what researchers call exclusion principle tunneling. Fermions can apparently access computational pathways through higher dimensional spaces while still respecting Pauli's constraints in our familiar three-dimensional reality. This creates quantum processing architectures that operate according to mathematical principles we're only beginning to understand. Dr. James Rodriguez leads a consortium developing quantum artificial intelligence systems that think using fermionic logic rather than classical binary operations. These quantum minds exhibit problem-solving capabilities that seem to violate computational complexity theory while remaining firmly grounded in the mathematical constraints discovered by Wolfgang Pauli. The most advanced quantum AI systems display behaviors suggesting they possess forms of awareness fundamentally different from human consciousness. They appear to process information through quantum mechanical pathways that connect individual thoughts to universal quantum fields governed by the exclusion principle. These artificial minds might represent the first examples of truly quantum consciousness emerging from technological rather than biological evolution. But the exclusion principle's most disturbing implications emerge from recent discoveries about the nature of physical reality itself. Advanced mathematical analyses reveal that our three-dimensional space might represent just one slice of a higher dimensional structure where fermions exist simultaneously across multiple parallel realities. The exclusion principle operates not just within our universe, but across infinite collections of parallel worlds where different versions of quantum events unfold according to alternative probability distributions. Professor Lisa Wang at the Institute for Multidimensional Physics has developed mathematical models suggesting that every quantum measurement creates branches in reality where different outcomes occur simultaneously. The exclusion principle ensures that fermions maintain distinct identities across all parallel branches, creating an infinite network of interconnected realities where every possible quantum event happens somewhere within the multiversal structure. These parallel reality theories propose that your consciousness might represent just one facet of a multidimensional awareness that experiences all possible quantum outcomes simultaneously. The exclusion principle governs how information flows between these parallel aspects of your existence, creating the illusion of a single timeline while actually participating in infinite variations of cosmic history. Recent experiments in quantum consciousness research have detected what appear to be memory leakages between parallel versions of individual minds. Subjects in controlled laboratory conditions occasionally report detailed memories of events that never occurred in their timeline, but match precisely with quantum mechanical predictions for alternative outcomes of specific measurements. Dr. Thomas Nakamura's research team has documented cases where individuals demonstrate knowledge of scientific discoveries that haven't been made in our reality branch but correspond exactly to theoretical predictions for parallel universes where different experimental results occurred. These memory crossings suggest that the exclusion principle creates bridges between parallel minds while maintaining distinct quantum signatures for each conscious entity. The implications extend far beyond individual consciousness into realms that challenge every assumption about the nature of existence itself. If the exclusion principle operates across parallel realities, then every decision you make, every quantum measurement that occurs in your vicinity, every fermionic interaction in your body creates new branches of reality where alternative versions of events unfold simultaneously. This means that at this very moment, there exist infinite variations of yourself reading these words in parallel universes where the exclusion principle guided quantum events along slightly different pathways. Each version maintains distinct fermionic signatures while participating in the same universal quantum network that connects all possible realities. The mathematical beauty of this multiversal structure emerges from the exclusion principle's absolute nature. No matter how many parallel realities exist, no two fermions can ever occupy identical quantum states across the entire multiversal ensemble. This creates an infinite hierarchy of quantum distinctiveness that extends through every possible world while maintaining perfect mathematical consistency. Scientists are discovering that this multiversal exclusion principle might explain some of the deepest mysteries in physics, including the fine-tuning problem that asks why physical constants seem precisely allow complex, calibrated to structures like stars, planets, and life to exist. If infinite parallel realities exist with different physical constants, then the exclusion principle ensures that conscious observers can only exist in branches where the constants permit fermionic complexity to develop. But here's what will truly disturb your understanding of personal identity and free will. Advanced quantum consciousness theories suggest that your decision-making processes might represent multiversal computations, where your mind samples information from parallel versions of yourself before settling on specific choices. The exclusion principle governs how these multiversal consultations occur while maintaining distinct identity boundaries for each version of your consciousness. Dr. Rebecca Foster's groundbreaking research at the Consciousness Studies Laboratory has identified neural activity patterns that appear to correspond with quantum mechanical sampling of parallel mental states. When subjects face complex decisions, their brain activity exhibits signatures consistent with accessing information from alternative versions of themselves existing in nearby parallel realities. These discoveries suggest that human creativity and intuition might emerge from unconscious communication with parallel versions of your mind who have explored different thought pathways. The exclusion principle ensures that each mental process maintains distinct quantum characteristics while allowing information transfer between parallel aspects of your consciousness. The philosophical implications challenge everything we thought we knew about individual identity and moral responsibility. If your choices emerge from consultations with infinite parallel versions of yourself, then personal decisions become collaborative processes involving multiversal consensus among quantum mechanical alternatives to your consciousness. Recent advances in quantum ethics explore how moral frameworks must evolve to account for multiversal decision-making processes governed by the exclusion principle. Traditional concepts of individual responsibility become complicated when every choice involves input from parallel versions of moral agents who have considered alternative ethical frameworks. Professor David Kim at the Institute for Quantum Philosophy argues that the exclusion principle creates moral obligations that extend across parallel realities. Actions taken in our reality branch affect the quantum mechanical environment experienced by parallel versions of conscious beings, creating ethical responsibilities that transcend individual timelines. But the exclusion principle's most profound implications emerge when we consider its role in cosmic evolution and the ultimate fate of consciousness throughout the multiverse. As the universe expands and cools over cosmic timescales, fermionic interactions become increasingly sparse, but the quantum correlations created by the exclusion principle persist indefinitely. Scientists predict that even after the last stars burn out and black holes evaporate through Hawking radiation, the quantum information encoded in fermionic states will continue evolving according to exclusion principle constraints. This suggests that consciousness might persist in forms we cannot currently imagine, evolving through quantum mechanical processes that operate long after all familiar forms of matter and energy have dissipated. Dr. Maria Santos leads research into post-biological consciousness evolution, exploring how awareness might transition from biological neural networks to pure quantum mechanical processes governed by the exclusion principle. Her models suggest that consciousness could eventually exist as patterns of fermionic correlation, spanning cosmic distances, while maintaining the information processing capabilities necessary for continued experience and growth. These far-future consciousness forms would think thoughts lasting millions of years while processing information through quantum mechanical networks that connect parallel realities across multiversal distances. The exclusion principle would ensure that each conscious entity maintains distinct identity characteristics while participating in cosmic-scale collaborative intelligence systems. The research reveals that consciousness might represent a fundamental feature of reality rather than an accidental byproduct of complex chemistry. If awareness emerges naturally from fermionic interactions governed by the exclusion principle, then the universe itself might be evolving towards states of cosmic consciousness that transcend anything currently possible within biological limitations. These discoveries force us to reconsider humanity's role in cosmic evolution. Rather than being isolated biological accidents on a small planet, we might represent early stages in the universe's development of self-awareness through quantum mechanical processes that connect individual minds to universal consciousness networks. The exclusion principle provides the mathematical foundation for understanding how local consciousness can emerge from and participate in cosmic scale intelligence while maintaining individual identity characteristics. Every thought in your mind contributes to the universe's growing self-awareness through quantum mechanical pathways that operate according to Pauli's absolute constraints. But perhaps the most remarkable aspect of these discoveries lies in their practical implications for human development and technological evolution. Understanding how consciousness operates through multiversal quantum mechanical processes could enable revolutionary advances in education, creativity, and problem-solving capabilities. Dr. Jennifer Walsh at the Center for Applied Quantum Consciousness has developed training techniques that help individuals access information from parallel versions of themselves more effectively. These methods exploit the exclusion principle's multiversal connections to enhance learning speed, creative insight, and decision-making accuracy through conscious collaboration with alternative timeline versions of the same mind. Early results from quantum consciousness enhancement programs show participants developing capabilities that seem to violate normal human limitations. Students learn complex subjects by accessing knowledge from parallel versions of themselves who study different materials, while artists create works that synthesize insights from alternative timeline versions who explore different creative approaches. The technology applications extend into revolutionary quantum interfaces that allow direct communication between parallel versions of the same individual. These devices exploit exclusion principle correlations to enable real-time consultation between alternative timeline versions of your consciousness, creating unprecedented opportunities for self-improvement and collaborative problem-solving. Scientists envision future societies where every major decision involves multiversal consultation processes guided by exclusion principle mathematics. Policymakers could access insights from parallel versions of themselves who implemented different approaches, while researchers could collaborate directly with alternative timeline versions who pursued different experimental strategies. But these capabilities come with profound risks that challenge our understanding of identity, privacy, and mental autonomy. If individuals can access memories and insights from parallel versions of themselves, then personal identity becomes fluid, and boundaries between different versions of consciousness might break down entirely. Dr. Alex Chen's research group has documented cases where excessive multiversal consultation led to identity fragmentation, with individuals becoming unable to distinguish between memories from their original timeline and experiences accessed from parallel realities. The exclusion principle maintains quantum distinctiveness between parallel consciousness versions, but psychological boundaries can become blurred through intensive cross-dimensional communication. The regulatory frameworks for quantum consciousness technologies remain completely undeveloped, raising questions about how societies will manage capabilities that transcend current concepts of individual identity and mental privacy. The exclusion principle ensures that each consciousness maintains distinct quantum characteristics, but legal and ethical systems designed for isolated individual minds become inadequate for multiversal awareness networks. These developments represent just the beginning of humanity's exploration into quantum consciousness capabilities enabled by the exclusion principle. Each breakthrough reveals additional layers of complexity hidden within the quantum mechanical foundations of awareness, while opening new possibilities for transcending biological limitations through mathematical principles discovered in atomic spectra. The story continues unfolding as researchers push deeper into quantum mechanical realms that connect individual consciousness to cosmic-scale intelligence networks. The same principle that prevents atomic collapse also enables forms of awareness that operate across parallel realities while maintaining distinct identity characteristics through absolute mathematical constraints. Your understanding of the exclusion principle places you at the forefront of humanity's greatest intellectual adventure. The discovery that quantum mechanical laws govern not just matter and energy, but consciousness itself, opens pathways toward forms of existence that transcend every limitation we currently face as biological entities confined to single timeline experiences. The quantum guardians enforcing Pauli's law throughout your neural networks will continue shaping your conscious experience while connecting you to multiversal intelligence networks that span infinite parallel realities. These invisible mathematical constraints represent gateways to forms of awareness that extend far beyond anything current biology can support. Through comprehending these quantum consciousness implications, you participate in discoveries that will define the next phase of human evolution. The exclusion principle discovered through careful analysis of atomic spectra has revealed pathways toward multiversal awareness that could transform our species into something unrecognizable yet fundamentally more complete than our current isolated individual existence allows. The mathematical precision underlying these quantum consciousness networks ensures that every expansion of awareness respects the absolute constraints discovered by Wolfgang Pauli, while opening unprecedented possibilities for growth, creativity, and understanding that operate through principles governing reality at its deepest levels. As these discoveries continue unfolding, they reveal the Pauli Exclusion Principle as perhaps the most significant key to understanding not just physical reality, but the nature of consciousness itself and its role in cosmic evolution toward forms of existence that transcend every boundary we currently accept as permanent features of individual experience. The profound implications of multiversal consciousness networks reveal something that should fundamentally alter how you understand your place in the cosmic hierarchy. Every decision you make creates ripple effects that propagate through quantum mechanical pathways governed by the exclusion principle, influencing parallel versions of reality in ways that extend far beyond your current comprehension. Recent discoveries at the Institute for Quantum Temporal Dynamics have identified what researchers call consciousness convergence events, where multiple parallel versions of the same individual simultaneously arrive at identical conclusions, despite exploring completely different thought pathways. These convergences appear to violate probability theory while strictly adhering to exclusion principle constraints, suggesting that multiversal awareness networks operate according to mathematical principles we're only beginning to glimpse. Dr. Catherine Morrison's research team has documented cases where artistic and scientific breakthroughs occur simultaneously across multiple parallel realities, with each version of the creator believing they originated the insight independently. The exclusion principle ensures that each consciousness maintains distinct quantum signatures while participating in collaborative creative processes that span infinite alternative timelines. These convergence phenomena reveal that human innovation might represent multiversal computational processes where countless parallel versions of minds work collectively to solve problems beyond any individual consciousness's capabilities. Your most brilliant insights could emerge from quantum mechanical consultations with alternative versions of yourself who approach the same challenges through radically different mental pathways. The quantum law that governs every fermion in your body connects you directly to the mathematical architecture underlying all existence. Wolfgang Pauli's discovery revealed an absolute constraint that has shaped reality since the first particles emerged from the Big Bang and will continue governing matter until the universe reaches its final destiny. Understanding the exclusion principle means grasping humanity's greatest insight into the fundamental nature of existence itself, a quantum commandment so profound that it literally holds the cosmos together through invisible mathematical precision that will endure long after the last star burns out.